So yeah, thanks for joining my session about in-memory OLTP in Microsoft SQL Server. So my name is Torsten Strauss. I'm a consultant, trainer, and speaker. I'm most valuable professional for data platforms since a while, and yeah, everything else is not that important apart from my website and my email address. So feel free to reach out to me whenever you have questions about performance tuning, because I would say exclusively focus on performance tuning, which becomes even more important in times of cloud, because people now realize that they can reduce cloud costs whenever you have a well-running SQL Server, right? So because you can lower the resources, so CPU, memory, and everything like this, and this means you can save money. So that means all the performance measurements you did in the past, you only did it because SQL Server or your users are complaining about slow performance. In these days, I would say it has a complete different impact to have proper performance tuning on a regular basis on a SQL Server, because again, you can reduce your resource consumption and therefore you can scale down your Azure or AWS or whatever resource to save money. So, and this is also the reason why I would like to talk about in-memory OLTP, because in-memory OLTP was introduced in SQL Server version 2014, if I remember correctly, with a lot of restrictions. So it wasn't, I would say, I do not want to say it was not usable, but you have a lot of restrictions, a lot of limitations. You wasn't able to set foreign key relationships and a lot of other things. So you only had a subset of supportive T-SQL commands. So I would say in 2014, it was not a product or an engine you could use. So this completely changed. So we are now in SQL Server version 2019. And you know, this kind of feature will evolve over time. And in-memory OLTP is definitely something which can boost your performance. I would not recommend to use in-memory OLTP for every project, every scenario, every requirement, because we will see later on there are specific reasons for using in-memory OLTP. This is, I would say, a complete different engine, a complete different architecture with pros and cons. But there is no silver bullet. There is nothing like we will go to in-memory OLTP and all your performance problems are gone. That is definitely not the case, believe me. I do not know whether I have enough time, but maybe in the end, because I just recognize that I have 19 minutes to present, which is really, really, really rare. I can show you cases when you do not have the right index on an OLTP, in-memory OLTP table. The performance, the select and the insert performance is horrible, horrible slow. 10, maybe 20, maybe even 100 times slower than the traditional engine. So, and this is why I never ever would recommend to use in-memory OLTP for every new project. Yeah. And before you think about migration, before you think about migrating your current traditional on-disk storage engine to an in-memory OLTP engine, you really have to know about the reasons why you should do this, because believe me, it is not an easy migration. Okay, so let's start with the code. So just need to understand how to minimize the window here. That works perfectly well for me. So I hope the size of the font is big enough so that everyone can see what I'm presenting. The problem is the bigger the size is, the more I have to scroll. So it is either scrolling or size of the font. Yeah. So I prefer to have a bigger font so you can read what I'm presenting, but I have to scroll a little bit more. Yeah. That's it. So as already mentioned, let me do the following. Yeah. As already mentioned, there are specific reasons to use in-memory OLTP. And mainly there are two reasons which we will, you can see the reasons, and we will go through the reasons, but you can see there are more than two. But especially from my perspective, and this is something which I can tell you already, avoid latches and locks, right? That is what really matters, and avoid locking and blocking. So, and maybe we can, and we will concentrate on the two reasons I already mentioned, and I personally find the most important one. But let us go through the entire list to understand what the idea of in-memory OLTP is and why Microsoft decided to create an entire new engine, which is a lot of effort. So by the way, the project was called Hackathon, and hackathon is, I think, is a Greek word for 100 times faster. So I like this kind of, I would say, challenges from Microsoft, yeah, telling us or telling the team, okay, we have to change to in-memory OLTP because we are aiming for a workload which can be processed by SQL Server 100 times faster than before. Believe me, it is possible, but it is never ever the usual performance increase you will see when you switch to in-memory OLTP. Okay, so the first reason for, again, for using in-memory OLTP is avoid physical reads. So, and just reading what I have written here, and will tell you or explain a little bit more whenever it makes sense. So the performance of reading data from memory, for sure, is much faster than reading from disk. This is what we know already. So you want to avoid physical IOs because physical IO is still the slowest operation within SQL Server. So whenever the buffer pool, and by the way, you have some kind of a buffer pool for memory OLTP, but it works completely different. But let's consider the traditional on-disk storage engine. So whenever you require pages from a specific table because you query the table, select all from table or whatever, SQL Server will look into the data cache, so in the buffer. And when the pages are available, SQL Server can directly get the pages from in-memory, which is not in-memory OLTP, but the pages are in memory already. So from that perspective, that means whenever we work with the traditional engine, comparing to the in-memory OLTP engine, for sure we have already in-memory pages in memory in our buffer cache. That means whenever your buffer cache is big enough to save all the data pages belonging to all tables within the database, it is very unlikely, I would say, that you will encounter physical IOs after the first time the page is written or read into the buffer cache. So, and this is something we already mentioned. So avoid physical reads, yeah, that is perfectly fine. But again, when you have enough memory in your environment, it is very unlikely that you will see physical reads. Okay, so sorry, the reason about the architecture of the so-called data or the buffer pool, which I already mentioned for the traditional engine, is because memory was expensive. 10 years back, memory was horrible expensive. Memory becomes affordable in these times. That means memory is not a resource, from a cost perspective, not a resource problem anymore. You can put more and more memory into your machine without spending, I don't know, $100,000. So, and therefore Microsoft was thinking, okay, when memory becomes much cheaper, so how can we use memory more efficient, right? So you can see that the in-memory OLTP, so this was the traditional engine, and these are the reasons why in-memory OLTP was evolved over time. So in-memory OLTP does not store data in on-disk data pages. Also, the data are not saved in buffer pool. That means there is almost, we will see it later, almost no read-write operation to your disk. Depends a little bit, when you create it, maybe you do not know, but I can tell you, you have two different options to create a table in a memory OLTP table with schema and data or schema only. So when you create your table, and this is something which we will see later on, when you create your in-memory OLTP with schema only, you accept that you will see a data loss whenever your SQL Server crashes. Because there's nothing like a checkpoint, nothing like this, nothing is written to disk. That means you will lose the entire data, which is perfectly fine when you have an ETL or staging area where you can always reload the data on demand. That is not an issue. But on the other hand, because you are not writing any information to disk, this is extremely fast, right? But when you want to rely on recovery and you want to make sure that even the in-memory OLTP data becomes accessible once SQL Server restarts after a crash, you have to send the information to your disk because memory will not outlast a SQL Server crash. So that means depending on the option, on the way you are creating your in-memory OLTP tables, again with schema only or schema and data, you have either no physical read or write, or you have physical read or write. You still also have impact to your transaction log, as we will see. I don't know whether we see it, I cannot promise. But believe me, you have still an impact to your transaction log whenever you have schema and data, so the second option, right? So this is something you have to take into consideration. So in-memory OLTP still reads and writes information to disk, yeah? Sometimes more, sometimes less information. So the problem about the buffer pool is you have a buffer pool manager. So think about the traditional engine. That means there are specific processes running in the background, which is the checkpoint and the lazy writer. I would say these are the two processes which are running in the background in order to maintain the buffer pool. So first of all, the checkpoint makes sure that the dirty pages will be flushed to disk. Yeah, if there's a write ahead logic for the transaction log, but not for the buffer pool. There's a checkpoint, which is a checkpoint process, which is running asynchronously, depending on your RTO and recovery time objective, which is 60 seconds. I think that's the default. And depending on the amount of data which are changed in buffer pool, so the amount of, or the number of dirty reads, the checkpoint will write the pages to disk in order to make sure that you do not have to wait forever when your SQL Server restarts. That is the only reason why we have to harden the data pages to disk in a traditional engine. And we have another process which is called lazy writer. The lazy writer is also an asynchronous process in the background, which looks into the buffer pool in order to decide, is there, I don't know, maybe 10, maybe 50% of space available, because it is very unlikely that someone asks for data pages which are not in the data buffer pool. That means when I have to make space available in the data buffer pool, when I read data from the, I would say, MDF or NDF file on demand, that means the user will have to wait until a space becomes available. That is the reason why the lazy writer is running in the background, and will from time to time analyze the buffer cache to see whether there is a need to flush a specific portion of the data of the data buffer pool to disk. So, and this has its own impact. This is physical I/O. That means it is a very comprehensive and also a very expensive process. This is something which can be completely avoided when you have something like in-memory OLTP. So the other, or it is also worth to mention that whenever you create an in-memory OLTP table, you have to have at least one index. Without having an index, you cannot create an in-memory OLTP table, because we will see later that in-memory OLTP will not save information on pages, 8 kilobyte size pages. Instead, all the information are sent in records, which is much more efficient, because now SQL Server can read one row instead of 8 kilobyte page, which is already much more efficient because we only have to read one row, not one page. But it only works when you have an index on top of your in-memory OLTP table, because there's nothing like an IAM page, so index allocation map page. There's nothing like a GAM page, global allocation map page, or PFS page, page free storage page.
Page free space, right?
Yeah, page free space page. That is always a little bit hard to, but you're right, PFS page. And so that means all this, the overhead related to the system pages are completely gone. But the only way to tell a record to which object, to which table it belongs, is now the index. Because we will see that we have an index chain between the records. It's not a doubly linked chain, it only works in one direction. That is the reason why you have to ensure that you select the right index with the right order, ascending or descending, because there is nothing like a doubly linked chain. There's nothing like a forward and backward scan. It is only forward scan, okay? So, but the indexes you create for an in-memory OLTP table are not saved to disk, and they are not part of the transaction log. That means index maintenance and everything like this is much more cheaper. And the indexes, whenever you restart your SQL Server, the indexes will be created from scratch again, because all the rows which are now, when you have a schema and data table, which are now coming from your disk, are now sent to the memory of SQL Server, and the index chain will now glue the records that you have one table in the end. So this is the index, but again, the index is never ever part of any physical operation. Okay, avoid latches and logs. So as already mentioned, this is definitely something where we will see a lot of advantages when using in-memory OLTP. That means whenever you see a high wait time on latches, then it is, or latches and latches and logs, which is, I don't know, wait, LCK underscore M underscore S U X or whatever. These are the wait times which are related to logs, and we have latches, which can be a page IO latch, which can be a page latch, or even really can be a latch. But here it is more about the page IO latches and the page latches. Yeah? So when you see a high amount of wait time on these wait statistics, and you do not have another solution to avoid them, to avoid logs is very hard, because in a SQL Server is running in read committed. So this is a standard transaction isolation level. That means whenever a record is read from a specific page, SQL Server acquires a shared log for this record. Once the record is produced, then the shared log will be released, and the next record will get the shared log. That means you will always end up with shared logs. The only transaction isolation level where you can avoid shared logs but not exclusive logs, is read uncommitted. But you know, read uncommitted means that you are willing to read dirty pages. This is something normally you do not want to have because we have to rely on ACID, the I and the C consistency and isolated, which comes or which is defined, yeah, I would say in the ACID rules itself. Yeah. So the problem about logs, I guess you understand, and I'm pretty sure you are familiar with logs because performance degrees is always a reason, or the reason for performance degrees is not most, but many times incompatible logs. So you will end up with so-called blocks, and the block will wait forever. Latches. What is a latch? And I guess we will see it later in the demonstration. A page latch means, in theory, you can run update statements on the same page by different threads at the same time. That means one thread will update record 1 in page 1, and the same thread at the same point in time, and not the same thread, another thread, but at the same point in time, tries to update the same record as well. That is the so-called lost update problem. That means the last thread will win. This is something SQL Server have to prevent from a physical structure. That means logging, you do not see a log. That is not a problem. You do not see a log. That still works because, or this is not the truth. Updating the same record, you will end up with a log. But okay, forget it. We will insert a record into a table. Okay, forget about the update, that was wrong, but inserting is right. I will insert a record into a page, and another thread at the same time will insert another record into the same page. That is definitely something which is possible. You do not end up with a block, right? Because you have an exclusive log on the first record, and you have another exclusive log on the other record I'm going to insert. So therefore, I do not have any kind of incompatible log, which means a block. But there are informations in the 96-byte big page header, which tells SQL Server where to insert the next record into the page, because this is the end of the payload. And SQL Server has to know this because otherwise it will overwrite the record which is already there. So this is the offset. That means it is nothing else than the position where SQL Server can insert the next record without overwriting an existing record. And this is something we need. The problem is now when we have more than one thread inserting data into the same page at the same point in time, the header information are read from both threads, and both threads will get the information, insert the record on. Position 96, which is the first slot after the page header, or 97, I don't know. So when this happens concurrently, we will end up with a lost update problem because the first record or the first thread will overwrite the second thread, or vice versa. It depends just on a nanosecond or whatever. Therefore, SQL Server have to acquire a so-called page latch, which is either shared, an exclusive, an update. We have a lot of page latches available, which are comparable to our logs, but this is completely different. Log is on a logical level. Latches, page latches, are on a physical level to protect, in our case, because it is a page latch, to protect the page. Because SQL Server have to ensure that the information where to save the next record, it has to protect the information as long as the first thread is inserting the record. Only when the insert is done and it is successful, the information about the new, I would say, end of the payload is written to the page header. And therefore, the second thread now knows about the position, where to insert the next record without overwriting the first information from the first insert. That is a problem about page latches. When you think about it, and this is something which is hard to avoid, because the more threads you have inserting into the same table at the same time, the more latch contention, page latch contention you will see. This is all, very typical in a last insert, I would say, page contention, which you always have when you insert in a table, in a clustered table or in a non-clustered index based on an ever-increasing key, like primary key identity 1.1. That means every new record is very likely that it will be inserted into the same page. So that means the right most page in your leaf level of your index balance tree becomes your bottleneck. So, but you know that in our current workload, in our current OLTP workload, it is very likely that we have more and more threads. The problem is the only way to solve this one is to think about, I would say, different or alternatives to create an ever-increasing key, for sure. But even if we are in a heap, we will end up with page latch contention, because again, SQL Server can insert this, I would say, records at the same time by different threads. So the only way to avoid this is to have faster CPUs, not more. More CPUs means it even becomes worse. Faster CPUs. And this is the problem. CPUs, they do not scale, as we know. Okay, we have very, very fast CPUs available comparing to, I don't know, 10 years back, but they are not as fast as they can completely eliminate the need of page latches. Page latches is, by the way, also something which you very often see in TempDB, because TempDB is nothing else than a database which is shared from all user databases at the same time. So therefore, SQL Server will create internal objects in the TempDB, which is nothing else than pages. So therefore, in a TempDB where you do not have even control about what is written to TempDB and what not, and when, because we have system processes, we have user processes, we have, I don't know, a hash match, which is spilling to TempDB. I don't know, there are several reasons that we will end up with a page allocation in TempDB. But again, we will see page latch contention on the pages, and for sure we will see page latch contentions on the so-called GUM page in the TempDB. That is a reason, by the way, why Microsoft recommend to use more than one physical TempDB file, because the GUM file has its own, I would say, interval, but this is not the problem here. The solution is, or not the solution, the solution is when you have more files in TempDB, you will end up with more GUM files. That means several threads now can allocate pages on several data files and therefore on several GUM pages. And the GUM page, therefore, is not your bottleneck anymore, because all the information about which pages belong to which object have to be saved in the GUM page. So your system pages become your bottleneck, right? So this is something which is completely eliminated in memory OLTP, because in memory OLTP is based on you can see it, multi-version concurrency control. There is no need for a lock. And because you do not even have a page, you cannot end up with a page latch contention. There is no page, there's just a record, which will be never ever touched twice. Or touched is the wrong word, modified twice. So, because again, we have multiple versions of records. Whenever I do an update on a record, SQL Server internally creates a new record. It will not update the existing record and mark the other record as, I would say, logically deleted. And later on, there's a garbage collection which will clean up all these rows, which are not needed anymore by any open transaction. right? We will see this. We have a begin transaction timestamp and we have an end transaction timestamp to invalidate a record. But again, the same record will be never ever updated again in in-memory OLTP. That is the reason why we will never ever end up with a latch, and we will never ever have locks. But we still can avoid dirty reads, because for the time the transaction starts, the record is the valid one, because it will just compare the current timestamp with the begin timestamp, which makes the record valid, of the record, and with the end timestamp. And when the current transaction is in between, this is a record to read. That means I have something like RCSI, read committed snapshot isolation, which works in a TempDB, which has its own impact. That is for sure a way to avoid locks in at least writer-reader, reader-writer locks in a traditional database engine. Yeah, but RCSI, I would say personally, there should be a reason why you should enable RCSI, so read committed snapshot isolation, because it has its own impact on the TempDB. Your inserts are much slower, and depending on how many versions of your records are currently exist in the TempDB, you will end up with a very slow read performance as well. This is not the case for memory OLTP. So avoid locking and blocking, I guess I already explained. Avoid CPU memory overhead for interpreted T-SQL commands, which is a stored procedure. Whenever I create a stored procedure, so the interpreted SQL stored procedure, that is a stored procedure, I'm pretty sure 99% of the stored procedures you currently write is the so-called interpreted T-SQL procedure. That means whenever you execute the stored procedure the first time, SQL Server will create an execution plan. There's an optimization phase, there's parsing, there's compiling, we have a memo structure. We have a lot of considerations. We have the cardinality estimator. We have different rules which are applied. And in the end, SQL Server presents a SQL execution or an execution plan to you, which is perfect. It is not the best plan. It is one of the best plan. It's the so-called good enough plan. But finding a good enough plan in a complex stored procedure has for sure impact on your I/O. That is the reason why SQL Server send all the plan information, so the instruction for the storage engine, how to process the data it will save it in the plan cache, in the procedure cache. So the procedure cache for sure have its own impact and everything like this. That means it is complex. We will lose IOs. And you can see them whenever you compile a query, you will see the compile time. That means the more often you compile, maybe because of new stored procedures, or maybe even because of, I don't know, your statistics become stale, you have a schema change in your table, you add a new index, whatever the reason is, SQL Server has to create an execution plan beforehand. Good. So in a natively compiled stored procedure, this is completely different. SQL Server, when you have in-memory OLTP tables, you have two ways to access data. And let me share this with you. Yeah. So you can see when I am on the left-hand side, which is the native compiled stored procedure, native compiled stored procedure only works with in-memory OLTP tables, because the way the table is designed is completely different. Again, we have rows, we have one index at least, we have an index chain, which only works in one direction. We do not have something like pages. It's a complete different way to access and to save data. Therefore, natively compiled stored procedure only works with in-memory OLTP table, which can be either schema only or schema and data. This doesn't matter. It's just a way to save data or not save data whenever SQL Server crashes. So, but there is a way to use an interpreted T-SQL command, yeah, so the usual stored procedure, to access data in an in-memory OLTP table by the so-called query interopt. That is possible. That means even just using in-memory OLTP tables, but do not migrate your interpreted sort procedure to natively compiled sort procedure, you already have the advantages of latches, at least latches, which is definitely something maybe is already worth to consider. So, but when you really want to access and get the best performance, you should use natively compiled sort procedure, which is nothing else, we will see this later, as is a C code. It is C code which tells SQL Server how to access the memory, I would say the, how can I put it, the memory space of SQL Server. It is an introduction on a machine level. It is not about, okay, we have different kind of operators here. Let's think about nested loop, hash match, or whatever. It is an interpretation on a C code level to tell SQL Server where and how to get the data from memory. Completely different. We will see that once a stored procedure, a natively stored procedure is compiled the first time, and it is compiled the first time even before you execute, just creating a natively compiled stored procedure means in the end, SQL Server will create, I will call it still execution plan, but in a C code. So that means the only way to create C code for natively compiled stored procedure is compile for unknown parameter values. Because again, SQL Server will create the C code even before the first execution of the stored procedure. There is no assumption, there is no estimation about the data which SQL Server have to process in a natively stored procedure, natively compiled stored procedure. That has its own, this is something which is, I would say, is a balance between the overhead of recompilation and everything like this and performance. Because SQL Server or Microsoft thinks that even if I assume or I execute or create in a C code, an execution plan for a natively compiled stored procedure based on unknown values, that is definitely much faster, even if it is not a perfect plan, than recompiling over and over and over again. Because again, every recompilation of a stored procedure means the user have to wait as far as you do not have an asynchronous recompilation, right? Which is possible, but for sure, sometimes the stored procedure have to be recompiled. Again, I/O, impact, memory, everything like this. So, and now maybe you wonder why this how this works when SQL Server do not know about the histogram, about density. And by the way, SQL Server knows still information, have still statistics objects for a memory OLTP table, but they are not used when SQL Server compiles the natively compiled stored procedure. So there is always one index, as mentioned already. And every in-memory OLTP index is fully covering. That means it really doesn't matter from a covering perspective if you have an index on column 1 or you have an index on column 2. Column 1 and column 2 or column 2 and column 1 is always part of your index chain. That is, every index is fully covering. You do not need to worry about bookmark lookups, yeah, key or read lookup, because every index is fully covering. There is no question about should I use an index or not. There is always an index which is fully covering. The only problem is when you add an index later on, then maybe this index is better because you decided for, I don't know, a hash index, yeah, which have a complete different structure. Then maybe it is worth to recompile your stored procedure because otherwise the stored procedure, natively compiled stored procedure, will not be recompiled and maybe therefore will not benefit from the new index. Okay, let's go back. And there's something I would say this is really worth to mention, maybe, but okay, this is a design principle. These are the design principles from Microsoft, right? So another principle or another reason to select in-memory OLTP is that whenever you have an interpreted stored procedure, not a natively compiled one, the assumption or the creation of the execution plan is based on the assumption that every page which you need to process the data for the query will be located on disk and they are not in buffer pool, because it is likely that you have data not in your buffer pool. So therefore, SQL Server always have to assume the worst case. That means the instructions for the storage engine and also the estimation, the IO cost, everything like this is based on the assumptions that your pages are not part of your buffer pool already, which is in modern systems often not the case anymore. That means your estimation is wrong because, again, it is a wrong assumption. And when an estimation is wrong, your execution plan can never ever be the best plan. So, and because, again, SQL Server will create a natively compiled stored procedure whenever you work with in-memory OLTP, there is nothing like, I would say, a best plan. There is an instruction to read data from memory. So there is no assumption that SQL Server have to read something from disk, because again, there are no data on disk SQL Server have to read for an in-memory OLTP table. There's nothing like this. There is no physical I/O. That means the plan which is created is always based on the assumption the data are in memory, not on disk. Okay, cool. So I already created a table beforehand, which have 5 million records, which is a copy of a big table which I created, which is a copy of sales order detail, some kind of a Cartesian product just to create a few records. So we will end up with 5 million records here for this specific table. And I added the clustered key. You can see, so, and the table looks like this. Just give you an impression. So this is just a small subset of the sales order detail table. You can see it here. And for sure, I'm not presenting 5 million rows. There's no reason to do it, just a subset of 100 rows. Okay, cool. What I will do now is the following. And this is so annoying. Okay, this is better. I will flush the buffer cache just to make sure that I do not have any data in my buffer pool, because currently we look into the traditional on-disk storage engine. For sure, I need to raise a checkpoint before in order to make sure that I do not have dirty pages, because dirty pages cannot be dropped from the buffer, because the dirty pages, first of all, have to written to disk. Okay, cool. Let's enable statistics IO and time. And let me do the following. I will execute this execution. No, the other way around. I will execute this query to see the execution plan. And it's just a count of 5 million rows. It takes, I don't know, you can see it here, maybe 16 milliseconds, 16 seconds, sorry. Yeah, perfectly fine. And that is nice because I forgot, sorry for this, but I enabled the execute. Okay, now it's visible. So the execution plans here. Perfect. I just executed one query. So an execution plan is created based on assumptions. We have estimations. Everything is based on estimations. So what we can see is that we have read. Yeah, last time it was a little bit less, but who cares? Yeah. So let's stick to this this KPIs here rather than now correcting all the CPU, all the statistics here. It is not worth, because in the end you will see it is still the same. If this query runs faster or slower, the next query which I will execute to compare will also run maybe a little bit faster, maybe a little bit slower than before. So, but who cares? The problem is the following. First of all, we can see the index, the clustered index scan. We can see the estimated IO cost, which is this time only 32. Last time it was the other way around. It was, sorry, it is 23. Last time it was 32. Okay, but again, who cares? It is, we only see that when I execute the same time the query, let me do it. all the rows, all the pages to be precise, are now in my buffer pool already. When I now revise the review the execution plan again, the estimated IO costs are still 23, whatever the unit is, let's say US dollar. Yeah, that's not true, because we do not have IO costs anymore. We have only logical IOs. That means it is neglectable. It is never ever comparable to physical IOs, because the first time I executed the query, we really had physical IOs to send all the pages to the buffer pool, which is a costly IO operation. The second time I execute the same query, SQL Server can now get all the rows from the buffer cache. So therefore, the estimated IO costs are completely wrong for the second execution of the same query. That is what I meant with suboptimal plans, based on the assumption SQL Server always have to get the rows from disk rather than from the buffer pool. What we can see is when we now query the buffer pool, this DMO is buffer descriptors, which we can use here. Let me execute this one. So what we can see, we should see, that's a little bit strange. Maybe 1 second. Did I mix it up for some reasons? Oh, come on, here. No, it is true. CronDB should work. I will give it another try. Nothing in. Okay, 1 second. I will execute the query another time. And maybe in the meanwhile, I can think about what the problem might be. Now we can see the data. Perfect. Because the lazy writer, we are already working on reducing, I think it's not a lazy writer. I don't know what happens, but we can see that, and this is, by the way, not the truth. It should be much more, but we can see that normally, don't ask me why this happens now. Maybe the adjustment to make sure that, sorry, I guess I can see the problem here. 1 second. Just need to connect to my instance. And maybe the problem is the memory allocation. Yeah, okay. Let's do this. Okay, but again, let's assume the following. I executed the query, and you can believe me, when I do the same exercise another time, next time, I'm pretty sure we will not end up with 900 rows. We will end up with 5 million rows. Okay, because every page, no, we have, no, this is right, sorry. We have 900 rows, and every row is 1 page. And for sure, we have 5 million rows, which are now, I don't know how many pages, how many rows we have on a page on an average level. I can calculate this one, but I'm not very good in math. But you can see I have almost 900 rows, 908 kilobyte pages in my buffer pool. That means I'm already allocating a lot of storage in my buffer pool just to count the number of rows in a table. Because the only way to count the number of rows in a table is nothing else than scanning the entire disk, the entire pages from disk or from my buffer pool. So what I also can do, and hopefully, because I added more memory, yeah, this is not the truth anymore. But believe me, again, if I execute this from scratch again with the right memory settings, we will see that the overall memory consumption, which is nothing else than 8 kilobyte multiplied with a number of pages, this is the memory footprint we already have. That means we have, the next time again, when I execute the same query, believe me, you will see 250 megabytes. We have 250 megabytes of 8 kilobyte pages just to count the number of rows for the big table here. Okay, let me do the following. Now I will create a database which supports memory optimized objects. And you can see how it works. We create a database This is I call it traditional part, you know already, but there is one file group, which can be whatever name, but it has to be defined as contains memory optimized data. Okay, this is how to create an in-memory OLTP database. And what you have to understand is that there is no need to just use the data failed, the operation, the system. Ah, that's nice. That's nice. 1 second. I know what happens. Sorry for this. I did the migration to the latest SQL Server version. Should be now. And the version is for sure 2009 SQL Server. I just need to change it one time. That is a problem when you do not do the exercise before the presentation another time. But I'm pretty sure I can fix this. Okay. Wonderful. Now we are on SQL Server 2019. Again, I will create the database. And again, by creating the database, I will allow the user to create in-memory OLTP tables. I do not force the user. That means you still have the alternative or the option either to create an in-memory OLTP object within the same database as you already have traditional on-disk tables. That means you can mix them up in the end. You can have both table objects in the same database, and for sure you can use natively compiled sort procedure and interpreted sort procedures in the same database, right? SAP HANA, for example, when you select SAP HANA, there is only in-memory OLTP, nothing else. Okay, that is already a big advantage because it is on you to decide when it makes sense to have an in-memory OLTP table. So let me do the following. I will now use the memory optimized database, and I will create a table. Exactly the same table as before. First of all, I create the schema, and you can see how it works. I have to have one index, and this one is a hash index, and I need to define a bucket count. I don't think I have time to cover this, but at least when you have a hash index, you have to define a bucket count. So that is just something which you cannot avoid for a hash index. So I create this one. Perfect. And I will drop a table in the tempdb just in case it is there. It is not there. But the problem now is the following, and this makes migration much more complicated because you cannot access data from one, you cannot access in-memory OLTP data or tables from one database by another database. That means cross-database in-memory OLTP access is completely, it's not allowed. It's not possible. So now let's think about the following. I want to get data from my AdventureWorks 2017 database in my memory optimized database. How can I do it? There is no cross-database access. There is nothing like select all from AdventureWorks 2017, insert into memory optimized database. This will not work. The only database sorry, you can use to exchange data between two databases when you use in-memory OLTP is the tempdb. That means I have to insert all the rows from the AdventureWorks database. You can see it here. It takes a moment into a temporary table, which is 5 million rows. It takes a moment. It's perfectly fine. And by the way, I will disable the execution plan. At the moment, there's no need for it. And now I have a copy of my data from AdventureWorks from this specific table in my tempdb. Okay, and now I can access the data from the tempdb table and get the data and insert the data into my in-memory OLTP table, into the schema I already defined. You can see insert into, this is the memory optimized table, and I get the data from the tempdb. This is an insufficient, this memory default run. Ah, nice, I like it. I like these kind of errors.
Hashtag hackathon problems.
You're right. This cannot be a problem about, no, it cannot be a problem.
Because it needs to create versions, right?
Maybe you just need to reconfigure because you changed the memory settings before.
You mean, yeah, I will give it another try. There's an insufficient system memory and resource pool. Ah, I get it. Yes, 1 second. I do not know whether I can, I wonder why this happens, because I already presented the code several times without any issues, but let me see whether there is, by
So
chance.
I think you changed the memory from 4 gigs to 8 gigs before, and maybe you have to just run reconfigure to sort of make those changes.
So you mean alter database? Alter database?
No, just type reconfigure.
No, this is
I'm not sure if
no, I do not, but okay, let's give it a try. If it is not working, I can for sure use all the information. You can see the information here. Honestly, I do not even have to run all the queries. It is still an insufficient memory because of resource pool default, and I guess this has something to do with my resource governor, because I know that I currently trying to create a session about resource governor, and maybe by chance I do some tweaks or changes here which are now not compatible with an in-memory OLTP workload like this. But no worries, this is really not an issue. And because I'm missing time anyway, I can go through the code. So now I have consider this works. I have all my data in the memory optimized database now. And when I run now the same query for an in-memory OLTP database, so you can see that the costs are, I would say, some kind of comparable, right? Because we are still using the interopt query to access data by a natively compiled T-SQL command from the in-memory OLTP table. So from a cost perspective, it is, I would say, the gain is neglectable. So, but you could see, if it works, that the index scan has now IO cost of 0. Because again, SQL Server now assumes that all the data are in memory. It means this is the IO cost, which are not there anymore, which makes the plan a little bit more less expensive. But again, remember, when the data are already in buffer pool, even a traditional engine, this should be the right costs. So the CPU time you can see here, and that is a good thing about the presentation. I do not even need to execute the code. Sorry for this. I really don't know what is going on here. But you can see that the CPU time is this one, comparing to the first execution, is maybe just the half. The elapsed time is also maybe just the half. That means just by using the in-memory OLTP table instead of a traditional table, we can already reduce the CPU time in this scenario by half, and the elapsed time also by half. When I now execute the same query, and this is what I can do because I do not have any pages in buffer pool, but you can believe me, even if I execute the query and it would work, we cannot see any pages in the buffer pool. Because again, we do not have data pages. So therefore we do not have a use of the buffer pool. All the pages, there are no pages, no buffer pool. So, but for sure, there is an impact on your memory. And the memory is something which you will see with DMDB XDP memory consumers. And you can do some joining here. And in the end, you will see that the allocated bytes is 64 megabytes for every bucket. So therefore we have a hash index. You remember the hash bucket here? Well, this is a definition. The bucket count. Every bucket count have 8 bytes. That means I can easily multiply 5 millions with 8 bytes. So that means we end up with 64 megabytes for the hash index. And then we have the row itself. The row itself have an impact of almost 400 megabytes. In the end, I use 462 megabytes for my in-memory OLTP data in memory. This is still the same memory. This is still SQL Server memory, right? Because it is considered, this is maybe also worth to mention. So whenever you configure your instance, you configure the memory as I did here. And the in-memory OLTP data are part of the maximum server memory, which is good because you have to limit the memory for the SQL Server on a host. But we are allocating 462 megabytes for an in-memory OLTP table. And for the row store, we just allocate 250 megabytes. That means the size is almost doubled for the same amount of information. This is something you need to think about. Memory is much cheaper, but it is still limited. So therefore, you really have to carefully look for the memory consumption of your in-memory OLTP table. Okay, so I can create a natively compiled stored procedure, which have, I would say, yeah, how can I put it? It's a template like this. So create procedure, name the stored procedure with schema binding, natively compilation. And then we have to say as begin atomic with transaction level. And we have 3 of them, as we will see, repeatable, read, serializable, and snapshot. It really depends what you want to see. And these kind of transaction isolation levels are completely different to the snapshot isolation level, the serializable and the repeatable read, you know, from the traditional engine. It is definitely different. Do not compare the transaction isolation levels here. They work different. So, and I think this is optional, the language US English. I don't know why it is even worth to mention here, but I think this is optional. But here, this is still the same T-SQL command. Some of the T-SQL commands are not supported for sure. But when I now execute, and again, sorry why this, I do not know, and I cannot fix it within a minute. Yeah, when you now execute the natively compiled stored procedure, and honestly, you wouldn't see any information more than this, we will end up with 300 milliseconds comparing to 700 milliseconds, which was the natively compiled stored procedure using in-memory OLTP data. And this is the interpreted stored procedure using the traditional on-disk storage. And this is also true for the user experience. The elapsed time, you can see it is for sure a single-threaded query. You can see the elapsed time is also increasing almost in the same way. That means the user experience is much better because we already reduced the query execution time from 1.5 or 1.6. Yeah, this is the elapsed time. Everything else is wait time. 1.6 seconds down to 300 milliseconds. That is great. So let me do some housekeeping. And hopefully the problem with the memory consumption is gone. But we will talk a little bit about latches and locks. So in the beginning, I already was trying to explain how a latch and how a lock looks like. And for the upcoming discussion, it is good to understand differences between latches and locks, because you remember the design principles: avoid latches, avoid locks, avoid blocks. So therefore, again, it is worth to remember what a latch is and what a lock is. Not on a very, or not on that level I already described, more or less just to compare them. So you can see the latch is something to protect the internal structure. In our case, the page latch is something which protects the page. That is a physical structure. The lock is applied on a logical level only. Again, we can change the behavior of the lock by setting a transaction isolation level. We can even run our entire database without any lock, only any shared lock to be precise, because the exclusive lock is always there. Even if I have read committed snapshot isolation, right? The shared lock is the only lock I can completely avoid, or I can, set the duration for the shared lock, not for the exclusive lock. Exclusive lock is nothing I can change. I can neither change the duration, I can neither say I do not want to have an exclusive lock. Latches are applied on a physical level, as already mentioned. So cheap to maintain. It's really just a matter of a few milliseconds. It really depends on the power of the CPU. And this is expensive to manage and maintain. If I remember correctly, the lock also have an impact of 96 kilobyte. I'm pretty sure this is still the same, because this is also the amount of the size which we will have for the page header. So that means the more locks you have in your system, and this is also definitely worth to mention, the more locks you have in your system, the more memory you allocate just for the lock with CK, not with G, for the lock manager. The more locks I have, the more memory is allocated. That is the reason why SQL Server implemented something like block escalation, because this is never ever the true, but let's make it very simple. When you have 5,000 rows, and again, this is not the truth, but we have to say something, some kind of threshold here, and it's very close to the reality. When we have 5,000 rows, SQL Server escalate the lock to normally to the table. Because think about the following: in the traditional engine, when you acquire more and more locks, every lock have its own memory footprint. That means when I exclusively lock a table with shared lock on every row, and consider you have a table like this with 5 million rows, that means we will end up with 5 million rows multiplied with 96 bytes. Again, when I run in repeatable read, for example, because a repeatable read means that SQL Server have to acquire the shared lock and is not allowed to release the shared lock until the entire transaction is either committed or rolled back. That means we will end up with 5 million rows multiplied with 96 kilobytes. You can, again, I'm not good at math, but maybe you know it better than me, but you can see the more rows we have in a table, the more rows or the more tables we have where we have to acquire shared lock in a traditional engine, the more I will have to spend, the more memory I have to spend for just locking the table. And this is something which we do not have in a memory OLTP. That means all the overhead for the lock with CK manager is completely gone. The duration of the latch is short. That is also why it is cheap. And this depends on the transaction, on the isolation level. And again, this is not true for the in-memory OLTP architecture. So the latches are not transaction-based, whereas the locks are transaction-based. So latches guarantee the consistency of in-memory objects, which is not only in-memory, it is not the in-memory OLTP object, it is some object which is in memory, which is, for example, a page in your buffer pool, right? Or guarantee the consistency. This is not true, and not only the in-memory objects, because we have page IO latches. This is on a physical level on the MDF or NDF file, right? So at least we protect a physical structure here. So, and lock is guarantee the transaction to be isolated and consistent. Nothing else than asset. So the C and the I. A is automatic, atomar, you know it better than me. And D is durability. But again, locks is just about isolation and consistency. Okay, I hope it works, the next demonstration. But before we will go to the next demonstration, we have to briefly touch which kind of latch modes we have. hopefully the next presentation will work. Then I can show you which kind of ledge we will see. And that is the reason why I want to explain the different ledge types up front. So we have shared ledge, which is compatible to the comparable, but not really comparable, but at least the meaning of the shared log is comparable. Ledge is comparable with a shared ledge, shared log. So shared ledge, shared log, because a shared ledge is used when the ledge is reading a page. Okay, then we have update. Yeah, for sure, we can already mention that is for updating. Exclusive means inserting, deleting, or whatever. It's very much the same as a log. So therefore, I guess you already get the idea. Then we have something like keep ledge mode, destroy ledge mode, and undefined ledge mode. Do not want to say do not worry about them, but normally you can neglect them. The you can ignore them. Sorry. You can see the metrics here, and the most important one is that the shared ledge is compatible with another shared ledge, but an update ledge is not compatible with itself, and an exclusive ledge is again compatible with no other ledge, as you can see here, apart from the keep ledge mode. I don't even know what it is. Yeah. So this is the interesting one. Yeah. And you can see this follows the same I would say rules as we will see when we have a log matrix, yeah, different logs. Okay, and we will consider the buffer ledges, which is buffer ledge are used to protect data pages inside the buffer cache, right? They are not only used for user-related data pages, but also for system pages like the PFS page, the GUM page, the SGUM page, and so forth. This is what I already mentioned in the very first beginning with the tempdb and last insert contention, everything like this. This falls underneath the page ledges. And then we have the page IO ledges. This is the physical protection of the MDF file to avoid that someone read a page from disk, and by the same time, at the same time, someone will write the page to disk. Okay. So what we can see is we have one wait stats. There is one DMV called DMOS wait stats, and we can filter. And by the way, we have a lot of more. We have now in SQL Server 2019, we have 1080 rows. It depends on the version. I remember something like 900 for SQL Server 2014. It's growing over time. But you can see that select all from DMO's wait stats, which is nothing else than the aggregated number of wait stats, which are aggregated since the SQL Server last restart, which is maybe 2 hours ago. Yeah, that is the reason why the numbers are quite small. We can filter them by ledge, and we can see that all the ledges I mentioned, page ledges, and page IO ledges, have its own weight statistic. Let me reset the weight statistic and hope it works. I will use AdventureWorks now, so the traditional database on this storage, and I will create a table like this. Create table, column 1, identity, ever increasing primary key, and we have a filler, just to make sure that I allocate a few more bytes than just 4 bytes plus 7 plus 2. So these are the internal bytes which I have to allocate for every insert. I just want to make sure that we have more than just one page when I insert a few thousand records here. I will clear the wait stats another time, and this should work. So let me go to the ostress page ledge 2, because what I'm going to do is I will use ostress to run this workload, which is defined here. And I will open the query in a moment. On 300 concurrent threads with an iteration of 100 times. So every thread of the 300 threads will execute the same query over and over again 100 times. So let me open the, I can do it from here. I can do it from the Windows Explorer. Yep, that should work. Perfect. Okay, it will. Okay, but no, that's fine. I was just thinking whether a new Management Studio application will open, but no, that's not the case. So insert into the table last page insert contention. That is a table which I created, and just use the default values. That means an ever increasing key, and we will end up with a filler of, I think, 500, 400, whatever bytes per row. So let me do this. Execute. What is wrong here? Again, execute CMD. My PC is horrible slow. I don't know whether this is caused by Zoom. I don't know, but it is not that fast. Okay, nevertheless, so I will execute this query now. And in the meanwhile, I didn't start it yet, but in the meanwhile, I will use DMO as a waiting task, which is nothing else than the current wait types for the current workload. Okay. It works, right? Yes, it works. Great. So we can see what happens. This will tell me the resource and the reason why SQL Server is waiting. So, and let's do the following. Let me copy one of the page here. This is a page address. This is database 5. Believe me, this is AdventureWorks 2017, which is not surprising because we are executing the query in the context of AdventureWorks 2017. 1 is nothing else than the file ID. This is in my case a primary file group because I have only one primary file group, or only one physical, one logical file group, and I have only one physical file attached to it. So I can easily replace now just a page. You can see this is a page. And what we will see is the following. So we will see the page because I'm currently dumping a specific page, which was marked as a resource SQL Server was waiting on. And you can see this is 1. I'm just getting the header with 0 because I can do it with 3 as well if you like, because maybe you have never ever seen a page. Yeah? So this is a page, this is a payload and so forth. So what happens is that SQL Server have to protect the page header information. And this is a page header. Everything else was just, I would say, interpreted. And this is nothing else than the memory address, but this is not, this is a real physical page. This one is about, this one is 96 bytes. We can for sure open a hex editor to see the hex code. I can use print option 1 to see the hex code, but this is not the intention of the presentation here. But here we have something which is M3 count. That is the position with in. Is this right? Yeah, it is right. This is the position where SQL Server can insert the next record. And because we have a clustered primary key with an identity, that means all 300 threads which are running 100 times in parallel, so concurrent, will insert into the same page over and over again, because SQL Server have to ensure that because of the structure of the balance tree, it will insert in the right order. So therefore, the rightmost page in your leaf of your balance tree becomes a bottleneck. And this was at the point in time where I took the snapshot of the weight statistic, the rightmost page. And if you remember, I can't do it anymore because we do not have any kind of waiting task at the moment, but you remember the page was repeating over and over and over again. All the threads were looking for the same access to write or to insert data into the page. So what we can,
Torsten, you have 10 minutes until the next.
I can see it.
Starts.
Yeah, I can see it.
Yeah,
I can
cool.
see it. Yeah, definitely. Sure. Yeah. So, and you can see this DMO's wait starts will now aggregate all the wait statistics. And we can see these. So one thread is reading from the page header, and another thread at the same time is writing to the page header. This is the traditional engine. This is per definition already a bottleneck, because we can see how much time we spend just on waiting on a page latch, right? So this is your overhead. And again, this is really hard to avoid just by having faster CPUs. So when I now execute the same, I think, let me do the switch. And I guess I can do it in 10 minutes and maybe even 9 minutes. You have some time to breathe. I will create the in-memory OLTP database again, just to have I would say a fresh scenario here. And I will use the in-memory optimized table or database. It takes maybe 15 seconds or even faster. So I will create the same table again, you can see, but this time I use a primary key non-clustered hash. So again, I need to have an index, schema data. I will clear the weight statistics, and I will run the same. And hopefully I'm not running into the same memory contention problem as before, because I don't know what the reason is. Sometimes it really helps just to restart SQL Server, but I do not have time for it. If it is not working, I definitely tell you what you should see. Let me execute this one. And when I now execute the DMO's weight stats, yeah, after, and I'm pretty sure this is all, no, it's not gone, it's not done. Wait for another, I don't know, 10 seconds or whatever, but you can see, and believe me, this is not getting worse. We will end up with no page latch contention, because again, we do not have something like a page available. You can see, and this is maybe definitely worth to open here, in memory, OLTP, to hash index, where I do have two here, two hash indexes. So this is what currently works. We have our hash table here, which is nothing else than the first address of the first record of the in-memory OLTP record. And you can see that we have the begin transaction timestamp and the end transaction timestamp. And what now happens is we are inserting more and more records into the row, but into the index, but we do not have a page. That means this record is never ever touched again. The only wait we will have, but this is just a matter of a few nanoseconds, is to update the hash index when we have a new hash index and the time it takes to create a new index link to the next record. That means, and I think I will stop here. That means whenever you have in-memory OLTP table and you suffer from page latches, you suffer from locks, you can see this is definitely the way to get rid of it, because of the complete different architecture SQL Server implemented for the in-memory OLTP table. So again, if you do not suffer from locks, if you do not suffer from latches, I wouldn't definitely, I know this is wrong. I do not want to say, I still want to say it is worth to consider in-memory OLTP, but there should be better reasons then to think about in-memory OLTP, because the main driver, for me at least, is locks and latches and nothing else. So that's it from my end. So there's so much more to cover. You can see this is nothing I can do within the next 7 minutes, even if I'm fast. But I hope you understand the design principles, the reasons why Microsoft SQL Server considers in-memory OLTP. You understand the benefits. And because you understand the benefits, it is much easier for you to decide when to use in-memory OLTP tables. That is what really is important.
Thank you. So that was interesting, and it would seem like a theme today to go on super nerdy topics and long sessions about digging into pages and locks and latches. And I'm going to say this is a useful refresher to me, if not just I wasn't perfectly clear on the difference between locks and latches, so that's cleared up. So I've learned that.
Great.
Yeah. Oh, we have a question. How much? How much it will be complex to have in-memory OLTP table with database and availability group. So I suppose the question is, how hard is it to put in-memory?
Yeah, so honestly, there is nothing you need to worry about. So in memory OLTP, for my understanding, in memory OLTP also works with high availability, yeah, so always on. And I think from that perspective, you do not need to worry about anything. I don't know, honestly, whether your data, your table can be defined as schema only. I don't know. That's a good question.
I'm gonna guess that because availability groups use log, log to distribute, you're gonna have to make it resident.
Yeah, I think so. That's a good question, a very good question. Yeah, I've never ever, and that is what I like about presenting, because I have these kind of smart questions, and this is another topic I will dive into, yeah, and maybe present the next time, but at least I will have a proper answer for you. So
Yeah.
sorry for this. Yeah, I think it is definitely possible, but I don't know whether the data have to be, the table have to be defined as schema and data, and not just, but not only schema. I don't know. Very good question.